Let's take another look at this example problem that we did in class of the father pushing the girl in sled up an incline. Okay, we're given the mass of the girl in sled, the coefficient of friction. We're told this is at constant velocity, so we're going to be in equilibrium. And what we're looking for is the work done by force applied. Now, the dilemma here is our force applied is horizontal, but the motion, the displacement, is up the incline. So we have two ways to look at this. I can find the force applied and multiply it by the horizontal distance that the sled is moving, or I can do this. I can just say that the displacement is the hypotenuse of this triangle, and then I need to just find this component of the father's push. I can take the push of the father, and I need to break it into two components, one perpendicular and one parallel to the incline. Now you can kind of pick your poison on this. Either way will give you the right answer. I could use a horizontal displacement and just multiply it by the force of push, or I can take this displacement along the incline and then find the force of the push parallel to the incline. It'll turn out the same way, but I think it's going to be easier to do this scenario. Okay, easy enough to compute the weight, and there's the force applied. Okay, what I need to do is I need to take the force applied and let's break it into components. I know this angle, so we're just going to express the force applied empirically, and there's our perpendicular and parallel components. All right, now let's take a look at force normal. Force normal is going to be comprised of two things. It's going to be, first of all, our perpendicular force of gravity and our perpendicular applied force. Okay, now I can compute force of friction. And I can also compute the parallel component of the weight. And there's force friction, 0.2 times our expression for force normal that we've already come up with. Okay, the first thing I'm going to do is I know that I am in equilibrium, both parallel and perpendicular. So I can go to Newton's law here, and I'm going to look at the parallel forces. And F net has to be equal to 0, so I come up with this expression. My applied force must be equal to my gravitational force minus, I wish I was using Camtasia. Okay, let me re-express myself for Newton's law. Newton's law says that I've got these three vectors, my force of the push parallel to the slope, my force of friction, and my component of gravity parallel to the slope. All these have to equal 0. So I just said that then the force of the push parallel to the slope has to be equal to the addition of force of friction in the parallel component of weight. All right, so we worked through the algebra. Remember, everything is expressed in components, and my unknown here is actually my force applied. All right, now that I've got my force applied, I'm almost there. Now we're ready to do our work equation, and I need to take then the force applied parallel to the slope in the distance applied parallel to the slope. All right, so I already have my expression for my force of push parallel to the slope. A little bit of trigonometry gives me the hypotenuse of the triangle, multiply the two together, and I get 2,300 joules. Not paying attention to significant figures, 2280. Okay, if you can handle this problem, you can handle just about any force and work problem. This problem was about 90% forces and about 10% working with the work equations.